Oh! Woo!
Oh!
Yay!
That's so. If you added more, it would definitely make sounds and pop. But yeah, you can hear it. Hey! Yes, I know.
Cool. Well, now that you know it works, tomorrow you can do it again, right? And
Yeah.
make another video.
Sweet.
Sweet.
All right.
Woohoo!
Welcome to our underwater fireworks video. Yeah, wow, it's cool.
It's awesome, guys. So we're gonna go over our materials and safety for our little diggy or whatever, and procedure. We'll do that all in one. So, guys, materials that we use, and I'll go over the procedure. Might as well while doing it. So, always wear your goggles. That is an important material. Okay, very important. So the first thing that we did was we had to set up our glass tubing. So for this you would just need like a long glass tube if you don't have one. And we bent it. So we needed a bent kind of hook shaped glass tubing and also small glass tube with it. And we needed a 1 liter graduated cylinder. We needed less than a gram of calcium carbide that we had in a little, tiny container. We needed 12 molar HCl for the reaction, and we needed a microtip pipette for the HCl, and you can use a small test tube, but we use a small flask to hold the KMNO4 and the HCl that creates chlorine gas. We also needed 1 gram of the KMNO4 and rubber tubing to connect to the glass tubing that will fit in here, and that will connect to this glass tubing that will go in here. That will, two gases mixed together will create the reaction. So initially our reaction was the KMNO4 being mixed with the HCl to create chlorine gas in this small flask right here that we put a 2-hole stopper on that's like covered with the pipette and the small tubing, and we connected the rubber tubing to this small little thing that was put into this stopper to connect the gases that will flow in here, where this is chilling in the water while the gas flows through here, the chlorine gas. We threw this calcium carbide into the 1 liter graduated cylinder to create sparks.
Wow, this is the safety part. Now, to be safe, we wanted to make sure we wore goggles at all times.
All times? All time. Wait,
Okay.
wear goggles at all times.
Okay, so for safety, we wanted to make sure that we kept our reaction in the fume hood, because we the first time didn't do that and realized the chlorine smelled very bad, and it over time actually just gave us a headache, and we were so sick of the smell of chlorine by the end of our demo making.
Yes.
Wear goggles to protect your eyes, of course, and make sure that all of the CaC2 has reacted, because if not all of the calcium carbide has reacted, you can't put it into the sink because it's not good for the tubing, and you never know like if it's gonna like react in the tubing still of the pipes and stuff.
Right.
Yeah.
3.
And be careful for the HCl.
Alright guys, so here's how we made our acetylene gas. So here is our calcium carbide, and we put that into the water that was in this large graduated cylinder, and initially that created C2H2 gas, which is acetylene gas, and then it also created CaOH2, but that's just aqueous, so it was just floating around in the water, but we didn't really see it. And you could see that when we dropped it in, it created bubbles, and you could actually see those bubbles. So there's acetylene gas for you guys. So for our chlorine gas, we had our KMNO4 in here, and then we also had our HCl. I might not see it in here, but it was a pipette, and we squeezed the HCl into the flask that had the KMNO4 already in it, and that created chlorine gas that we had. And for that chlorine gas to get to the graduated cylinder, we had a small tube sticking out of the flask, and our rubber tubing connected to that small tube that connected to our larger tube that was in the graduated cylinder, and that initially flowed the gas through all of those glass tubes and rubber tubes into the graduated cylinder, and you'll see in our next slide how that reaction happened with acetylene and chlorine together.
It is time for the acetylene and the chlorine to combine and collide and create heat and light. Here is the light, and it also formed heat. You could kind of feel it was getting hot. Could you? No, you couldn't. Oh, yeah.
I mean, you could like feel it kind of like on the graduated cylinder, but you know, it wasn't that big. The more you mostly saw the light, and we didn't really focus on the heat that much.
Yeah. So when acetylene and chlorine combined, the chlorine and the acetylene were both present because the chlorine was there, and then the acetylene was formed from when the calcium carbide was dropped in, and they needed to collide in the correct orientation so that they produced heat and light. And so then as the reaction proceeded until all of the bubbles have risen to the top, they kept reacting with each other, and you could see the heat and light, and it just almost looked like fireworks to you, you know. And you'll see a video, or and so then basically it went on for like a few minutes, and that's how we saw the fireworks, and it was great.
In order for you to understand how the gas particles combine, it is important to know collision theory. And collision theory is when molecules react, they must collide in the correct orientation and with more kinetic energy than the activation energy of the reaction. Essentially, this means that they need to combine at the perfect time and the perfect way so they collide. And you could see here in our little diagram, we have our C2H2, which is our acetylene gas, and our CO2 gas, which is our chlorine gas, combining together, and initially that would create, you know, the sparks that you saw in our demo video before this video.
To understand better what activation energy is, we need to look at phase diagrams. Now, this is an exothermic phase diagram because it goes from reactants to products and it loses heat. Now, there's the activation energy is the energy before the reaction transitions from reactants to products. Right here you can see this is the activation energy, it's the transition state. And the amount of energy is normally much higher at this state. You can see the jump up here, and which is why in order for a reaction to occur we need the catalyst so that it can speed up the reaction and make it easier to happen. And catalysts speed up the reaction because they lower the activation energy, meaning that the reaction requires less energy in order to go from reactants to products. If the particles in the gas don't collide, then it will result, cut that out, right?
Okay.
And so then we see that this is the activation energy, but right here, after the catalyst, the activation energy is much lower, which means that the reaction is going to be a lot easier to go over this one rather than over this one. So that's why oftentimes catalysts are used, and in our reaction we used HCl as our catalyst. We have two examples that Mina beautifully drew.
So if you guys didn't understand completely what was said in the last one, here's an easy example. So you can see that this man is trying to push this boulder down. The boulder is like it takes a lot to push, right? And so this is basically the energy that he's already using, and it takes a lot of energy for him to push this boulder down this hill. But when you add a catalyst to it, say another person, while they're both pushing on the boulder, it's putting more energy, it lowers the amount of energy that this first person had to use, and it makes this boulder go down the hill. To make better sense of how the heat and light is actually being given off, you need to understand that this reaction is an exothermic reaction. So, an exothermic reaction is a process in which the system gives off heat and light. As you can see here in our example, we have a fire. It's not a hand. Anyways, a fire.
It doesn't look like a hand
anymore. Fire gives off heat, right? So this is basically generally, a nice little example. And here's our energy diagram. As we explained before, you can see that it starts off with a lot of energy, and then it gives off its heat, so it loses its energy,
Instead of releasing heat, endothermic reactions absorb heat and light. For example, ice takes in all of the heat, causing the water or drink around it to become cold.
So, when we look at underwater fireworks, since the reaction between acetylene and chlorine gases are exothermic, a product will be heat and light, causing you to see what we perceive as fireworks underwater. What?